All right, I think we should move on to our next speaker. This was an awesome discussion. Thank you, Dave, as always. I think Dobromir is up next.
Yep.
Hello. Ah, there you are.
So I just share my screen.
Yes.
Here we go. And okay.
There we go.
Just a second, I'm sorry. Okay, so we're ready to go, right? Okay. Well, thank you very much. This is an awesome series of talks. I'm very glad that I'm here to listen to this. And so I think a lot of us can agree, I suppose, that AI, traditional AI, cannot deliver on all of its promises. And I pulled this from the website. Alife could offer some insight and ideas given the shared history and common approach between the fields. So I'll just offer you my suggestions, and you can tell me at the end if they make sense or not. To cut straight to the chase, I'm just going to summarize very briefly right at the beginning. So we suggest developing some things following a principle where we emphasize dynamic interaction instead at the expense of autonomy and generalization. And I think that's kind of part of it. This statement is very, I think, obvious. Another part might be a little controversial. I don't know. You can tell me if it's a crazy idea to de-emphasize autonomy and generalization. The method that we found that what we could say about how we develop things in this context, in retrospect, is reverse self-organization. I think it's just a convenient term to describe how we proceed in the lab. And finally, I'm going to be using examples from human movement and things that might one day become rehabilitation robotics applications. So, can we call this dynamic, interactive, artificial intelligence? Now let's go into a little bit in the history. At the theoretical level, we don't have new principles. Actually, there's so much work that I don't have time to go over all of it. I'm just going to list all the relevant approaches that we've seen, especially here. From adaptive behavior, balanced part, self-robotics, embodied intelligence, enactive, etc., all the way to social enactive robotics. One thing that I see as common in all of this is that we look to exploit, we want to set up the system in such a way that it exploits emergent dynamic patterns, the interaction between agents. So we'll start just with that. And to see how this would compare to a more traditional typical approach to AI, at least what it tries to be, in the one case you would have, the goal is to reproduce human capacities and the system to be autonomous and generative. Whereas we suggest, well, maybe it's good to start simple and just extend human skill, not even try to be autonomous, instead of rely on interdependence, and maybe allow for a bit of open-endedness at the end. These were my examples at the beginning from a popular movie, The Two Kinds, just as an example, but I think it's more productive to look at this additional discussion, the implications of these two approaches. On the one side, let's say on the left side, the scenario, what a self-driving vehicle tries to be, if they arrive at being as autonomous as they want to be, basically it will be something like an artificial organism, at least that's what it's trying to be. And it's autonomous to the extent that it actually takes agency from us. As a passenger, you go in and it takes you somewhere, and at that point you won't even know how you got there. So from something that allows us to do things, it actually takes agency from us. On the other side, it might be more productive in the short term to instead create machines that simply augment our capacities, allow us to see further, move in different ways. Importantly, this allows us, at least for some time, to consider these very difficult ethical and philosophical consequences of the fully autonomous approach. Okay, so if we want to have fully autonomous agents, then we have to respond to the ethical and philosophical, what is agency, what is intentional. And this seems very difficult. So maybe we can take more gradual steps. So about the method, I think it's illustrated very well by something that I saw yesterday during one of the talks. We can discuss if reverse self-organization in the lab makes sense, but it makes sense to me. So I retroactively just use it on things that I and colleagues are doing. I'll give you two examples from my work, which are much, much more simple and modest. But what's interesting is that they involve human behavior. So in the one case, it was part of a project where we wanted to optimize rhythmic auditory cueing for Parkinson's disease. Very briefly, why we need to do this is the condition is associated with these gait symptoms that are at least a little bit alleviated by auditory cueing. Participants have a reference. And maybe it would work better if the cueing is interactively synchronized to the steps of the participants. In the past, what colleagues did was they were too aggressive with the synchronization. They forced the synchronization. So we suggest let's not force that. Let's just allow this to happen organically. So we develop our paradigm by kind of modeling the context, using in the one case this just a single phase oscillator with two parameters: the rate at which the beat of the stimulus likes to go and how much it responds to the participants' steps. And we just make this gross assumption about the dynamics at the gate level of the participant. So we can set some of these parameters. We know roughly how fast the participants like to walk. So you just don't know one parameter. Using this, we can set up the system in the ballpark. So we don't need to force synchronization. We just say how much will be the minimum coupling so that synchronization is possible spontaneously to happen. One more detail, we're driving the stimulus. It tries to be a little faster than the participants. So we want to see the effect. The effect will be if participants responding spontaneously in train, they will be increasing their cadence. This is kind of what the setup looks like at the beginning. I'll go straight to the important result. Here you have this comparison between different conditions of the stimulus. You have two non-interactive and one very forcefully synchronizing stimulus. The third one, the third bar, is the condition that I described to you, the interactive cueing that makes spontaneous synchronization possible, but doesn't force it. And on the right side, you have the patients. On the left side, you have the healthy. In both groups, you have the most increasing cadence. In the third condition, that's the interactive cueing. So we're very happy. We're very happy because without asking participants to synchronize, without telling them to try harder or anything, they were not explicitly, purposefully trying to synchronize. We managed to produce the synchronization effect, and we also managed to take them to a little higher cadence. So all of this happens spontaneously. We just kind of set constraints. And this is something that is potentially a little bit useful from a clinical perspective, because if patients practice their gait, then it's good for them. Now, next example is from a different project where we tried to make, in this case, young, healthy adults acquire beneficial motor variability by interacting with a chaotic system. And you say, why on earth would you do that? First, that's not how we describe it to them. We just told them, you'll be playing music with a drunk artificial partner. So the drunk partner is kind of periodic, but a little bit variable, which creates a little bit of difficulty. Why we want to introduce variability is because it's beneficial, but we're not totally sure how to do that. So just adding randomness to the parameters of a training task or some kind of sports or in the rehabilitation context doesn't necessarily always produce the effects that we would like. So let's find a cleverer way to introduce variability. The way to do it is effectively what's happening, even though participants don't think of it that way, is they're trying to learn to control a chaotic system. And that's possible because a chaotic system, as you see on the right side, has these so-called unstable periodic orbits. So even though it's chaotic, if you have some information about the system and you have some ability for feedback, you can keep it on the unstable periodic orbit. In this way, you synchronize and control it. And you can think a little bit also this as an extension, kind of more complicated version of a double pendulum control that's popular in robotics and also to some extent human motor control. How we set this up? It was an auditory motor synchronization. The participants modulated the pitch of this sound that they heard on one side of their headphones. And in the other side, they heard a partner, which was also a modulated pitch continuously, driven by the chaotic system, in this case, the true oscillator. Importantly, in the interactive condition, there was weak coupling as well, so that participants could figure out with practice how exactly to move, how to try to synchronize these two, so that they're not only synchronized, they're driving the chaotic system into a more periodic behavior, which you can see here in the last row, comparing early on the left side and late practice trials in the three conditions. So we have a control condition with periodic stimulus, one with the chaotic but non-interactive, and the one that I'm describing and focusing on is the interactive chaotic. As you can see towards the end of practice, participants are not only synchronizing, they're also driving the stimulus into a more periodic orbit. So they have learned how to do this. So that's kind of we think, a very useful learning task. And just to verify that that's across all participants, you can see the stats for synchronization. The dark band is the interactive chaotic. They tend to increase. The variability of the stimulus in the interactive chaotic tends to decrease over practice. That's because participants are managing to make it more periodic. And also with the transfer entropy, which tends to increase over practice trials in the interactive chaotic condition. So the part that is, aside from the thing that in theory is beneficial, is that participants are producing variability and they're working with variability and unpredictability. We wanted to look at one more thing, which is new. We figure out that would be interesting for the present discussion, is how they actually did it. It turns out that participants could do it in two different ways without us telling them. They could settle on a period one trajectory. So here you see relatively flat series of amplitudes and periods of the stimulus cycle. And at the bottom, you see this up and down of the amplitudes and the periods, which is because in this particular trial, this particular participant managed to drive the stimulus into a period two. Importantly, this is not something that I've explained, but this being a chaotic system that's underneath the whole stimulus, it has multiple different ways of being controlled. It has multiple different unstable periodic orbits. So it affords this variability, and participants can discover and settle on something that is convenient for them. And you can also see it in a distribution, especially in the high scoring trials, the red distributions. You see that participants tend to split into two modes, corresponding to the two period one and period two modes of this chaotic stimulus. And to conclude now, I've shown you two examples of something that we think can be described as dynamic interactive artificial intelligence. There's some very small but practical benefit to it, exploiting this emergent coordination. The way we did it, although I have to admit, we used this label retroactively, is we reverse self-organize this. We looked at what parameters will make this possible, will allow participants to discover this pattern of coordination, and without explaining everything, without forcing them, allow this to happen. At least in some cases, I think it's useful to start minimal and just focus on trying to make what Tom calls interactive organs instead of fully autonomous organisms, which is a very, very high bar. It's, I think, for everything, that might be one of the conclusions, is that we maybe try too hard, and always for generalization and autonomy. Like I said, this avoids some of the ethical and philosophical problems for some time associated with full autonomy. And we can still have a little bit of open-endedness. And finally, that's also, I think, important, is now that we have this system, it does something where we can allow it to learn. We can actually start implementing different forms of adaptation or learning on the system side, on the stimulus side, which again, I think it's kind of consistent with a more Alife approach, where to have evolution, you first need something that is like a system that has a functional interaction of some sort with its environment, which may be easier like that than to try to aim straight for the most sophisticated, most autonomous system, yet, however, we don't even know if we can get there. And that's the end of this talk.
Very great. So maybe a little round of applause for a speaker. Anybody who wants to ask a question can either raise their hand, post in the chat.
Yeah, can I ask a question?
Absolutely.
Yeah, thank you. Thank you, David. Great work, as always. So my question is a very technical one. So you showed that two different cases, the period 1 and the period 2 attractors. And what is the criteria to distinguish between period 1 pattern and period 2? Because their difference is kind of subtle, right?
Yes, you're right. So this is I rely more on the fact that there are two distributions. That was a bimodal distributions of this was the entropy, was a way of showing that the trajectory is more curvy or less curvy. I rely more on that. They never really perfectly, at least in this case, because we only had 40 training trials. If we had done this for longer, maybe they'll be able to perfectly settle on just one and keep it consistently for the whole trial. What actually happens is they kind of go in sync, they control it, but then they lose it because it's an unstable kind of coordination pattern, right? So in fact, they're never just one or just two.
Yep, that makes sense. Thank you very much.
Which again is kind of what drives us. We think for all these theoretical ways that's beneficial for the participants is to be kept at an unstable point the whole time, and they have to really try all sorts of different strategies and movements to it's an organic way of introducing this variability.
Yep, thank you.
All right, any other questions? Okay, we have a question in the chat. Kingston, if you want to go ahead and read your question. If not,
sure, I just had my fan on. It was really hot and loud. But anyway, do you make a distinction between the artificial organ and a prosthetic device? Do you think this chaotic dynamics of the time giver has more of its own agency in comparison to other like pacemaker devices?
So the first part of the question, well, thank you for the question, for the two questions. The first one, that's kind of exactly where we think we're going. I'm not sure. I mean, these are very loose definitions. We came up with this weeks ago, basically, or maybe months ago. So part of me giving this talk is just to probe how people feel about it. But that's kind of generally, that's the idea, is that prosthetic devices, we can retroactively call, you guys, you have been doing dynamic interactive artificial intelligence. You don't know it, but you can actually use this label. Maybe. So that's kind of the project, is to allow these fields that exist in the periphery of AI to think of themselves as a form of preliminary, very early AI. So for the second question, has more of its own agency in comparison to other devices. I'm not sure I can answer this the best way. Something that I think I can say is, and that's in relation to your talk, we kind of, with Tom Freuse, my collaborator, we thought of this as a system, at least the coordination pattern itself has this condition of precarity, it's precarious. So we thought that something that has precariousness, actually that's one of the things that we have to take into consideration when thinking of systems with agency, agents with agency. So maybe because this thing has it's more precarious, especially the second, not the first one. The first one is very dumb in a way. The second one is very precarious. Maybe you could use this to develop an arm that it has more agency, although that's, I don't know, I'm just making this up right at the moment. You're muted, but
yeah, things can go wrong in more interesting ways in your systems. Thank you.
Cool, thank you. Do we have any final questions that people want to ask? I would like to say shout out to Matthew Egbert's group, who seems to be all together in one place, enjoying food like collaboratively, which is something that the rest of us would have taken for granted in maybe February, but now really deeply miss. So enjoy yourselves for all.